What if the greatest explosion in history never ended? What if, instead of fading with time, its echoes grew into a roar, a crescendo building across 14 billion years? We are born of that explosion, you and I. Every atom in our bodies, every planet, every star is a fragment of a single infinitely dense point that ignited, unfurling the very fabric of space and time. We call it the Big Bang, but the name is a profound deception. It suggests a singular event, a cosmic firecracker that went off its show now long since over. The truth is far more dynamic, more unsettling. That primordial detonation is still happening. Right now, the universe is expanding. The space between galaxies is not an empty stage on which things move. It is an active stretching medium, an unseen river carrying everything along with its current. Galaxies, those majestic islands of light, are not flying away from us through space. Rather, the space between us and them is being created moment by moment, stretching the distance, red-shifting the ancient starlight into a mournful ruby glow. For most of human history, and for most of cosmology's brief life, we believed we understood the governing principle of this cosmic epic: gravity. It is the master architect of the cosmos, the great collector. Gravity gathers dust into stars, sculpts stars into galaxies, and corrals galaxies into magnificent, sprawling superclusters. It is the cosmic shepherd, relentless and patient, always pulling things together. Given this immutable fact, the universe's ultimate fate seemed a simple matter of accounting. On one side of the ledger, the fading momentum of the Big Bang, that initial outward push. On the other, the cumulative, unyielding gravitational pull of every speck of matter and energy in existence. The expansion, we reasoned, must be slowing down. Like a ball thrown into the air, it had to lose speed, pulled back by the immense gravity of the whole. The only real question was how it would end. Would gravity win decisively, pulling everything back together in a cataclysmic, big crunch, a fiery rebirth, or would the expansion coast forever but ever more slowly, the universe fading into a cold, dark and lonely eternity, a big freeze of unimaginable stillness? This was the grand, somber narrative we told ourselves, a story of a universe winding down its initial energy spent. A story that made perfect, elegant sense, and it was completely, utterly wrong. The revelation came not with a triumphant shout, but with a confused whisper, a flicker in the data that refused to go away. In the late 1990s, two competing teams of astronomers embarked on one of the most ambitious projects ever conceived. They sought to measure the precise rate of the universe's deceleration by looking at the most distant objects they could find, type Ia supernovae, the violent death throes of white dwarf stars. These cataclysms are what we call standard candles. Because they all explode with nearly the same intrinsic brightness, their apparent faintness from our perspective on Earth tells us exactly how far away they are. By comparing their distance to the redshift of their light, the astronomers could create a map of cosmic expansion stretching back through billions of years of history. They were in effect playing the universe's history in reverse, expecting to find a younger cosmos that was expanding much faster than it is today. They would pinpoint the exact moment gravity began to win. The telescopes gathered the faint ancient light. The data was collected, cleaned and analysed, and then confusion turned to disbelief. The numbers were not just wrong, they were impossible. They were backward. The most distant supernovae, the ones that showed us the universe of the deep past, were dimmer, and therefore farther away than they had any right to be. This could mean only one thing. In the intervening billions of years, something had pushed them faster and farther than any model predicted. The expansion of the universe was not slowing down, it was accelerating. The ball thrown into the air wasn't falling back down, it had ignited rockets and was screaming away into the void. Imagine the shock in those labs, the frantic search for error, a mistake in the code, a flaw in the telescopes, a fundamental misunderstanding of supernovae physics. Every alternative was explored, every possibility exhausted. But the conclusion was inescapable, confirmed by both teams independently. Our universe is not winding down. It is revving up, driven by a mysterious repulsive force that seems to emerge from the vacuum of space itself. To this inexplicable universe-spanning engine of anti-gravity we gave a name born of our own profound ignorance: dark energy. a name that is less of an explanation and more of a confession. It is the dark, not just because it is unseen, but because it resides in the deepest shadows of our understanding. It makes up nearly 70% of the total energy density of the cosmos, yet we have no idea what it is. It is a ghost in the cosmic machine, a phantom pressure that is pushing the universe apart at the seams. It is the most profound mystery in all of science, a discovery that rewrote our past and completely redefined our future. For 2 decades, our picture of this force, as bewildering as it was, had one comforting quality: simplicity. We operated under an assumption, a foundational pillar of modern cosmology known as the cosmological principle. It states that on the largest scales, the universe is homogeneous and isotropic. In simpler terms, it's roughly the same everywhere and in every direction. No matter where you are in the cosmos, you should see the same basic structure, the same laws of physics, the same story unfolding. By extension, dark energy. The dominant component of this universe had to be smooth. It was envisioned as a constant and unchanging property of space-time itself, a gentle uniform pressure distributed evenly through every cubic centimetre of the void, from the space between your atoms to the gulfs between superclusters. This assumption was elegant, it was tidy. It allowed us to build models that described the universe as a single coherent whole, evolving under one predictable, albeit mysterious, influence. Our cosmos was a perfectly inflated balloon, its expansion accelerating smoothly and uniformly in all directions for all time. Our destiny was again written in the stars, no longer a crunch or a freeze, but perhaps a big rip, where the acceleration becomes so powerful it eventually tears apart galaxies, stars, planets, and even the atoms from which we are made. A terrifying, but at least a predictable end. But what if that pillar of simplicity is a lie? What if the smooth, placid ocean of dark energy has currents, eddies and storms? What if the ghost in the machine is not a gentle presence, but a restless, shifting entity? For years there have been whispers at the edge of our perception, anomalies in our data that we tried to explain away, a strange, large-scale cold spot in the cosmic microwave background radiation, the afterglow of the Big Bang itself, a subtle, inexplicable alignment in the axes of quasars across billions of light years, an unnerving tension between different methods of measuring the Hubble, constant the universe's current expansion rate. One method using the early universe gives one number, another using the local modern universe gives a slightly but stubbornly different one. It was as if the universe's cosmic metronome was ticking at a different speed here and now than it was far away and long ago. Each was a breadcrumb, a small, unsettling clue. But now those breadcrumbs have led us to something astounding, something that challenges the very foundation of our cosmic worldview. A new high-precision mapping of the movements of nearby galaxies has uncovered a deviation from the expected cosmic flow, a disturbance far too large and coherent to be random. It's not in some distant, unknowable corner of the cosmos. It is here, on our doorstep, in our own cosmic backyard. The evidence points to a staggering conclusion. We may be living on the edge of a colossal bubble, not a bubble of matter or of anything we can see. It is a bubble in the fabric of reality itself. A vast localized region of space, perhaps billions of light years across, where the density of dark energy is different from the cosmic average. A kind of low-pressure zone in the ethereal substance of the vacuum, a place where the rules of cosmic expansion are subtly but significantly altered. This is not merely an interesting celestial discovery, it is a cosmological earthquake. The idea of lumpy dark energy shatters the elegant simplicity of our most successful models. It means the cosmological principle, our belief that the universe is the same everywhere, might be fundamentally wrong. It suggests that the universe is not a single, monolithic entity unfolding according to one grand universal script. Instead, it could be a patchwork of different domains, each with its own local flavour of cosmic repulsion, each with its own unique destiny. The implications are almost too vast to grasp. If dark energy can pool and thin out, then our predictions for the ultimate fate of the cosmos are not predictions at all. They are just possibilities, local weather reports in a universe filled with unknowable climates. Perhaps in one region of the cosmos the acceleration will lead to a big rip, while another starved of dark energy will collapse under its own gravity. And yet another might coast into a gentle freeze. The grand singular destiny of the universe dissolves into a kaleidoscope of potential futures, and the most urgent, the most profound question shifts from, what is the fate of the universe, to a much more personal, much more terrifying one. What is the fate of, a corner of the universe? This bubble, this anomaly in the cosmic order is no longer a distant abstract concept. It is the environment in which our Milky Way lives and moves. Its unique properties are shaping the evolution of our local group, and its gravitational influence may be tugging on us right now, setting our destiny on a path different from all others. We have been like islanders who believed the entire world was a calm, predictable sea, only to find we are adrift in a complex ocean of hidden currents, great maelstroms and unfathomable tides. The discovery of this structure has thrown open the door to a new, wilder and far more complex cosmos than we ever dared to imagine. It's a universe that might not just be strange, but parochial, and we are left with the most unsettling of questions. What lies at the heart of this cosmic bubble? What forces created it? And is it growing or shrinking? And most importantly, are we on the inside looking out, or are we on the outside looking in? The answer could change everything we know about our past, our present, and our ultimate future in the cosmos. What if the most profound truth about our universe was born from what a genius considered his greatest mistake? For millennia, we gazed at the heavens and saw permanence and eternal and unchanging clockwork of stars. This comforting idea of a static cosmos was so deeply ingrained in our thinking that even Albert Einstein in the early 20th century bent his own revolutionary equations of general relativity to fit it. His theory naturally predicted a dynamic universe, one that should be either expanding or contracting. Unsettled by this, he introduced a mathematical fix, an extra term he called the cosmological constant. It was a kind of cosmic anti-gravity, a fudge factor designed to hold the universe perfectly still, balancing it on a knife's edge against its own gravitational pull. He had crafted on paper a timeless and elegant cosmos. But the universe, it turned out, had far more dramatic plans. Out on a remote California mountaintop under the immense dome of the Mount Wilson Observatory, another story was unfolding. Here, astronomer Edwin Hubble was undertaking a task of almost unimaginable scale to map the true geography of the cosmos. For nights on end, in the cold, silent dark, he guided the colossal Hooker telescope, then the largest in the world, capturing faint smudges of light from what were then called spiral nebulae. These were mysteries, their nature and distance a subject of fierce debate. Were they clouds of gas within our own Milky Way, or were they, as some dare to speculate, entire island universes, adrift in an ocean of emptiness far beyond our own? To solve the puzzle, Hubble needed a yardstick, a way to measure these staggering distances. He found it in a special class of pulsating stars, the Cepheid variables. These stars are cosmic metronomes, their intrinsic brightness directly linked to the rhythm of their pulse. By measuring their period, you could know their true luminosity, and by comparing that true brightness to how dim they appeared from Earth, you could calculate their distance. It was the crucial first rung on a new cosmic ladder. One by one, Hubble measured the Cepheids within the Andromeda Nebula and other spirals. His calculations were definitive. These were not local clouds. They were galaxies, magnificent star systems like our own, millions of light years away. That discovery alone would have secured his place in history, for in that moment our universe expanded from a single galaxy into a vast archipelago of billions. But he didn't stop there. He began analysing the light from these distant galaxies, and he found something bizarre, something systematic and deeply strange. The light was stretched, its wavelength shifted towards the red end of the spectrum. This was the Doppler effect, the same phenomenon that lowers the pitch of a receding ambulance siren, but applied to light itself. A redshift meant the galaxy was moving away from us, and the further he looked, the more pronounced this redshift became. The relationship was undeniable. The more distant a galaxy, the faster it was racing away. This was the observational proof that shattered the static dream. The universe was not a fixed and eternal stage. It was a single colossal event, a performance in progress. Every galaxy was flying away from every other galaxy, not through some empty container, but because the very fabric of space-time itself was expanding, carrying them along for the ride. Imagine dots on the surface of a balloon as it inflates. From the perspective of any one dot, all the others appear to be rushing away. There is no centre to this expansion. It is happening everywhere at once. Einstein, upon hearing of Hubble's discovery, visited him at Mount Wilson. He looked through the eyepiece, saw the evidence with his own eyes, and declared his cosmological constant, his attempt to freeze the cosmos, the biggest blunder of his life. He had failed to believe what his own mathematics had been telling him all along. Humanity now faced a staggering new reality: our universe had a history. If everything is flying apart now, then in the distant past, everything must have been unimaginably close together. The idea of the Big Bang was born from this simple, backward extrapolation of Hubble's law. Yet this profound discovery immediately posed an even deeper question, a question that would dominate cosmology for the next 70 years. What is the universe's ultimate fate? We now knew the cosmos was born in a fiery instant and has been expanding ever since. But would it expand forever, or would the collective gravity of all the matter within it, the countless stars, the gas, the dust and the galaxies, act as a colossal brake, gradually slowing the expansion down? For decades, this was the central drama. On one side, you have the initial outward momentum from the Big Bang, the cosmic starting gun. On the other, you have gravity, the universe's relentless architect, tirelessly pulling everything back together. The fate of everything depended on the victor of this cosmic tug-of-war. The answer astronomers believed hinged on a single crucial number, a value they called omega. Omega represented the total density of matter and energy in the universe. If the density was high enough, greater than a specific critical density, then gravity would eventually win. The expansion would slow halt and then reverse, pulling all of existence back together in a final cataclysmic Big Crunch, a fiery bookend to the Big Bang. If, however, the density was too low, less than the critical value, gravity's pull would be too feeble. The expansion would slow but never stop. The universe would coast onwards forever, its galaxies growing ever more distant, its stars eventually burning out, leaving behind a cold, dark and eternally empty expanse known as the Big Freeze. There was also a third knife-edge possibility. If the density was precisely equal to the critical value, if omega was exactly 1, the universe would be perfectly balanced. It would expand forever, but at a rate that asymptotically approached zero, slowing for all eternity, but never quite stopping. To many theorists, this flat universe was the most elegant and mathematically beautiful solution. So began the Great Cosmic Accounting Project. For generations, astronomers tried to weigh the universe. They counted galaxies in deep field surveys, they measured the rotation speeds of spiral arms to infer the mass of the invisible dark matter, halos surrounding them. They analysed the gravitational lensing of distant quasars. They were attempting to put all the matter on a scale to see if it was enough to halt the expansion. The work was painstaking, fraught with uncertainty. The answer always seemed just out of reach, hovering tantalisingly near the critical value, but never settling definitively on one side or the other. It was clear that to truly settle the debate, we needed a new way to look back in time. We needed to measure the expansion rate not just now, but deep in the cosmic past to see for ourselves how much gravity had slowed things down over billions of years. The key arrived in the form of the most violent events the universe has to offer: exploding stars. Specifically, a very special kind of stellar death known as a Type Ia supernova. These are not the typical explosions of massive aging stars. A Type Ia supernova happens in a binary star system where a small dense remnant called a white dwarf greedily siphons material from a larger companion star. This dead star gains weight molecule by molecule over millions of years until it approaches a precise critical mass known as the Chandrasekhar limit, about 1.4 times the mass of our Sun. At that exact point, the pressure at its core becomes so immense that it triggers a runaway thermonuclear reaction. In an instant, the entire star detonates with unimaginable fury, briefly outshining its entire host galaxy with the light of 1 billion suns. The beauty of this mechanism is its uniformity. Because every one of these supernovae is triggered at the exact same mass, they all explode with almost the exact same intrinsic brightness. They are standard candles. If you see one of these celestial lighthouses in a distant galaxy, you know precisely how bright it truly is. By measuring how faint it appears to us, we can calculate its distance with unprecedented accuracy, far beyond the reach of Hubble's Cepheids. They were the perfect cosmic mile markers scattered throughout space and time that could finally allow us to chart the history of cosmic expansion and measure the breaking power of gravity. By the 1990s, two rival teams of astronomers armed with powerful new digital cameras and telescopes embarked on a race to find these faint, distant explosions and solve the question of the universe's fate. On one side was the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. On the other was the High Z Supernova Search Team, a global collaboration led by Brian Schmidt from Australia and Adam Rees in the United States. The work was a grueling marathon of observation and analysis. They would scan vast patches of the sky, take an image, and then return weeks later to take the same image again. Then, using powerful software, they would compare the two, looking for a single new point of light among billions of stars, the telltale sign of a newly exploded supernova. Once a candidate was found, it was a frantic race against time to use the world's largest telescopes to confirm its nature and measure its redshift before it faded away forever. Both teams were working under the same assumption. They expected to find that the most distant supernovae, the ones whose light had travelled for billions of years to reach us, would appear brighter than Hubble's simple law would predict. This was because in the past, the universe would have been expanding more slowly than it is today, so the supernova wouldn't have been carried as far away from us as a constant expansion model would suggest. Their goal was simply to measure the magnitude of this deceleration. They were trying to quantify precisely how hard gravity was pulling on the cosmic brakes. But then, as the data trickled in, something felt profoundly wrong. Perlmutter's team was the first to get a statistically significant result from a handful of supernovae, and it was baffling. The numbers just didn't make sense. Adam Rees, analysing the data for the other team, was encountering the same bizarre anomaly. The most distant supernova they were finding were not brighter than expected. They were dimmer, consistently inexplicably about 25% dimmer than they had any right to be. The initial reaction on both teams was one of self-doubt. There had to be a mistake. Perhaps their calculations were wrong. Maybe their detectors had some subtle flaw. Or perhaps the supernovae themselves were the problem. Could it be that ancient supernovae were intrinsically fainter than more recent ones? Or maybe there was some kind of intervening cosmic dust, some grey intergalactic smog that was blocking the light and fooling them into thinking the explosions were farther away. They spent months trying to find an error, desperately attempting to explain away the result. Every potential explanation they investigated led to a dead end. The data was clean. The calibrations were correct. The supernovae, both near and far, appeared to be perfectly reliable standard candles. There seemed to be only one conclusion left. A conclusion so radical, so contrary to a century of cosmological thought, that no one wanted to believe it. The only way for these supernovae to be so consistently dim was if they were farther away than all of our models predicted. Farther away than they should be, in a universe that was coasting, and certainly farther away than in a universe whose expansion was slowing down. For them to have travelled so much farther, the expansion of the universe could not have been slowing down over the last several billion years. It must have been speeding up. The implications were earth-shattering. It meant that the cosmic tug-of-war was not being won by gravity. It wasn't even a draw. Gravity was losing. Some other force, a mysterious repulsive energy inherent in the fabric of space itself, was pushing the universe apart at an ever-increasing rate. The cosmic brakes weren't on. The accelerator was being flawed. When the two teams finally published their results in 1998, the world of cosmology was thrown into a state of profound shock. The discovery was so counterintuitive, it felt like throwing a ball into the air and watching it shoot upwards faster and faster into the sky. It violated everything we thought we knew about the cosmos and its governing forces. The universe wasn't destined for a big crunch, or even a gentle big freeze. It was careening towards a state of ultimate isolation, a big rip, or a heat death, where every galaxy would eventually be pushed beyond our horizon, leaving our own Milky Way alone in an endless observable void. Suddenly scientists had a universe filled with an unknown substance, a cosmic ghost pushing everything apart. What could it be? In a moment of supreme historical irony, they looked back to Einstein's biggest blunder. His cosmological constant, the term he had invented to create a static repulsive force to counteract gravity, was suddenly resurrected from the dustbin of history. It was the perfect mathematical description for this newly discovered phenomenon, a constant energy density woven into the vacuum of space itself. As the universe expands, more space is created, and with it more of this repulsive energy, causing the expansion to accelerate. This mysterious entity was given a new name, a name that perfectly encapsulated our ignorance of its true nature: dark energy. Its existence fundamentally redrew our map of reality. The universe we now understood was composed of far less than we ever imagined. All the matter we can see and interact with the stars, the planets you and me, makes up a paltry 5% of the cosmos. Another 25% is cold, dark matter, the invisible gravitational scaffolding that holds galaxies together. And the vast remainder, a staggering 70%, is this enigmatic dark energy, the engine of cosmic acceleration. This new recipe for the cosmos, known as the lambda cold dark matter model, or lambda CDM, became the standard model of cosmology. It has been stunningly successful, able to explain the cosmic microwave background radiation, the large-scale structure of galaxy clusters, and of course the accelerating expansion with remarkable precision. Yet, it is a model built upon two colossal pillars of ignorance. We don't know what dark matter is, and we have absolutely no idea what dark energy is. The cosmological constant, while it fits the data, is also a theoretical nightmare. When our best theories of particle physics try to predict the energy of the vacuum, the number they produce is catastrophically wrong. It's about 120 orders of magnitude larger than the value we observe. This is widely considered the worst theoretical prediction in the history of physics. Furthermore, we seem to be living in a very peculiar cosmic era. For most of cosmic history, the universe was dominated by matter and gravity was in charge. In the far future, dark energy will be completely dominant. We just happen to be alive in the brief transitional period where the density of matter and the density of dark energy are roughly comparable. There's no known reason why this should be the case. It seems like an absurd coincidence. Despite these deep unsettling problems, the lambda CDM model rests on one simple foundational assumption that has guided all of our research since that revolutionary discovery. It assumes that dark energy, whatever it may be, is the cosmological constant, that it is a smooth uniform energy field perfectly distributed throughout all of space. Its density is the same here as it is in the most distant galaxy. Its repulsive force was the same 1 billion years ago as it is today, and it will be the same 1 billion years from now. It is the unchanging, immutable background of our accelerating reality. For decades, this has been our map of everything, the bedrock upon which our understanding of the universe's destiny is built. A map that assumed the darkness was uniform. But what if the map is wrong? What if the bedrock is beginning to crack? What if the darkness isn't the same everywhere? And so with the discovery of cosmic acceleration, we believed we had finally read the universe's grand design, the lambda cold dark matter model. Our standard model of cosmology was a towering intellectual achievement, a recipe for the cosmos that seemed to explain everything from the afterglow of the Big Bang to the graceful dance of galaxies across billions of light years. It was elegant, it was powerful, and its predictions were confirmed again and again. For a brief shining moment in human history, it felt as though we had solved the ultimate puzzle. We had balanced the cosmic ledger with just enough dark matter to build the structures we see, and just enough dark energy, this perfectly smooth, unchanging cosmological constant, to drive the expansion ever faster. The universe, it seemed, was beautifully, reassuringly simple, but the universe rarely obliges our desire for simplicity. Deep within the torrents of data streaming back from our most sensitive instruments, buried beneath layers of statistical noise, a whisper of rebellion began. It was not a sudden shattering contradiction, but something far more unsettling, a persistent low hum of dissonance, a series of tiny inconsistencies that on their own could be dismissed. Yet when viewed together, they hinted that our perfect cosmic model was perhaps not so perfect after all. The first clues came not from looking at the vast empty spaces between galaxies, but at the galaxies themselves. According to our model, the expansion of space should be uniform in all directions, a majestic isotropic tide carrying everything with it. This is the Hubble flow, the great cosmic river on which all galaxies are adrift. Of course, galaxies are not passive corks bobbing on this current. They feel the gravitational pull of their neighbours clustering together into groups forming immense superclusters and falling into the gravitational wells of even larger structures. This local motion, distinct from the overall cosmic expansion, is what we call a peculiar velocity. For decades, cosmologists had painstakingly worked to measure these velocities and subtract them from their observations, peeling away the local chatter to hear the pure uniform hum of the expanding universe beneath. The process is a masterpiece of celestial mechanics and patient observation. It demands the use of standard candles, astronomical objects with a known intrinsic brightness, like the pulsing of Cepheid variable stars or the cataclysmic uniform blaze of Type A supernovae. By comparing how bright they appear to how bright we know they should be, we can calculate their distance with astonishing precision. Once we have the distance, we can measure the galaxy's redshift to see how fast it's receding from us. The trick then is to see if that speed matches what the Hubble flow predicts for a galaxy at that distance. If it doesn't, the difference is its peculiar velocity, the signature of local gravitational tugs of war. For years, these peculiar velocities appeared random, a chaotic jumble of galaxies being pulled this way and that, precisely as expected in a universe filled with lumpy clusters of dark matter. But as our catalogues grew encompassing hundreds of thousands of galaxies, a ghostly pattern began to emerge from the chaos. Some astronomers scrutinizing vast swathes of the sky noticed something strange. It seemed that entire collections of galaxies, vast streams of them spanning hundreds of millions of light years, were moving in a coherent direction that could not be explained by the pull of any known supercluster or massive structure. It was a form of cosmic synchronized swimming on an impossible scale. This was the so-called dark flow, a subtle but statistically significant drift, a gravitational undertow pulling everything in a specific direction toward the constellations of Centaurus and Hydra. The implications were staggering. Our model, the one that had worked so well, had no room for such a thing. It would require a gravitational anchor of unimaginable mass, something so large it would have to lie beyond the edge of our observable universe, its influence reaching back to us across the cosmic horizon. The idea was outlandish, and the scientific community was deeply skeptical. The measurements were fantastically difficult, prone to subtle biases and systematic errors. Perhaps the standard candles weren't so standard. Perhaps dust within our own galaxy was dimming the light in ways we hadn't accounted for. For every study that found the flow, another found nothing, chalking it up to a statistical fluke. Yet the anomaly refused to vanish completely. It lingered in the data, a stubborn, inconvenient truth that hinted at a fundamental crack in the foundations of our cosmic understanding. While astronomers were grappling with the unruly motions of galaxies, another group of scientists was staring at a much older mystery, a picture of the universe in its infancy. They were studying the cosmic microwave background, the CMB, that faint pervasive glow of radiation left over from the Big Bang. This ancient light, which has travelled for 13.8 billion years to reach our telescopes, is a snapshot of the universe when it was just 380,000 years old. On this baby picture, we see the seeds of all future structures, tiny fluctuations in temperature and density that would eventually grow into the galaxies and clusters we see today. The standard model of cosmology makes a very firm, non-negotiable prediction. About this light on the largest scales, it should be almost perfectly uniform. The minute temperature variations should be randomly distributed across the entire sky like a perfectly shuffled deck of cards. The universe, after all, has no special direction, no up or down, no preferred axis. When our first dedicated CMB satellite COBE mapped this ancient light, it found exactly that a universe of breathtaking isotropy, confirming the model's predictions with stunning accuracy. Its successor, the Wilkinson Microwave Anisotropy Probe, or WMAP, gave us a far sharper image, a beautiful speckled oval that would become an icon of 21st century science. And it was here in this exquisitely detailed map that the ghosts first appeared. As scientists analysed the data, applying incredibly sophisticated statistical tools to search for patterns, they found features that shouldn't exist. There was an enormous patch of sky that was anomalously cold, a cold spot far larger and deeper than random fluctuations should allow. It was a cosmic bruise, a chilling void where there should have been warmth. Was it a statistical fluke, a 1 in 1,000 chance possibly? But there was more. When they analysed the largest patterns of fluctuations across the entire sky, the longest wavelengths of texture on this cosmic drumhead, they found them to be strangely aligned. They seemed to line up with the plane of our own solar system, a feature dubbed the axis of evil, for the trouble it caused theorists. This was cosmological heresy. It was as if the entire universe knew about our tiny insignificant corner of the Milky Way. How could the structure of the cosmos on the grandest scales possibly be correlated with the orbital plane of Earth? It made no sense. It violated the Copernican principle, the very idea that we do not occupy a special place in the universe. The team behind the WMAP satellite spent years trying to hunt down the source of this anomaly. They checked and rechecked their instruments, their analysis methods, their models of foreground contamination from our own galaxy. They looked for every conceivable error that could produce such a bizarre result. They found nothing. Then came the European Space Agency's Planck satellite, an instrument of even greater sensitivity and precision, designed to settle these questions once and for all. It would produce the definitive map of the early universe, erasing any lingering doubts or instrumental artifacts. The global community of cosmologists held its breath. When the Planck data was released, it was a triumph. The map was breathtakingly beautiful, a stunning confirmation of the standard model down to the smallest details. But as scientists looked closer, their unease returned. The anomalies were still there. The cold spot was real. The strange alignment, though slightly less pronounced, persisted. Planck had not erased the ghosts. It had captured them in high definition. The debate raged. Many argued these were simply a posteriori statistics, that if you look hard enough at any random dataset, you are bound to find strange patterns. It's like seeing faces in the clouds. You notice the interesting ones and ignore the countless others that look like nothing at all. Yet others felt a growing dread. Perhaps these were not flukes. Perhaps the universe was trying to tell us something profound, that one of our most cherished assumptions, the perfect isotropic symmetry of the cosmos, was wrong. These anomalies, the dark flow and the CMB alignments, were subtle esoteric puzzles debated largely in the hushed halls of academic conferences. But a third crack was emerging in our cosmic model, one that was far more direct and impossible to ignore. It became known simply as the Hubble tension, and it would grow into a full-blown crisis in cosmology. The Hubble constant H0 is arguably the most important number in all of cosmology. It tells us how fast the universe is expanding right now, and for a model to be considered successful, it must be able to accurately predict this value. The problem was we had developed two entirely independent and exquisitely precise ways to measure it, and they were beginning to give us two different answers. The first method looks to the early universe. By using the incredibly detailed data from the Planck satellite's map of the CMB, we can run our standard model of cosmology forward in time. We take the initial conditions of the universe input, our best understanding of physics, dark matter and dark energy, and the model predicts what the expansion rate should be today. It's like measuring the exact size and weight of a newborn baby, and using a trusted growth chart predicting its exact height at age 18. For years, this method gave a consistent value for the Hubble, constant a number with astonishingly small error bars. It was a testament to the power of our theories. The second method looks to the late universe. It is a more direct approach to the painstaking work of building what astronomers call the cosmic distance ladder. It starts close to home, measuring the distances to nearby galaxies using those reliable Cepheid variable stars. Then we find galaxies that are farther away but are close enough to have both Cepheids and a type Ia supernova. This allows us to calibrate the true brightness of these supernovae. Once calibrated, we can use these brilliant exploding stars as standard candles to measure distances to galaxies billions of light years away. By measuring the distance to these galaxies and their redshift, we can calculate the current expansion rate directly. It's a brute force measurement of how fast things are flying apart right now, akin to going out and actually measuring the 18-year-old with a tape measure instead of relying on the prediction. For decades, the error bars on both of these measurements were large enough that their values overlapped. The growth chart prediction and the direct measurement were in statistical agreement. But as our technology improved, as the Hubble Space Telescope and ground-based observatories gathered more and more data, the error bars began to shrink. And as they shrank, a horrifying gap opened up between the two values. They were no longer in agreement. They were in stark, undeniable conflict. The early universe prediction from Planck gave a slower rate of expansion. The late universe measurements from supernovae consistently gave a faster one. The discrepancy wasn't small. It grew to a statistical significance known as 5 sigma, a threshold in particle physics that signifies a genuine discovery. This was the gold standard. It meant there was only a 1 in 3.5 million chance that this difference was a random statistical fluke. The scientific community was thrown into turmoil. This wasn't a subtle alignment or a strange flow. This was a direct quantitative contradiction at the heart of our model. It was as if our trusted growth chart was systematically, fundamentally wrong. Something was missing from our understanding of the universe's history. An unknown ingredient, a new physical law, or a dramatic cosmic event must have occurred between the time of the CMB and today to alter the expansion rate. Physicists scrambled for explanations. Perhaps there was a new type of energetic particle in the early universe, a dark radiation. Perhaps dark matter wasn't so cold and simple, but had strange interactions. Perhaps our theory of gravity itself, Einstein's general relativity, needed to be modified. Or perhaps the explanation was tied to the most mysterious component of all dark energy. Our model had been built on the assumption that dark energy was a cosmological constant, that its density was perfectly smooth and unchanging in both space and time. It was the simplest possible explanation. But what if simple was wrong? What if the peculiar velocities of galaxies, the strange coldness in the CMB and the irreconcilable tension in our expansion rate were all pointing to the same revolutionary idea? What if the repulsive force tearing our universe apart was not a uniform placid sea, but a dynamic churning ocean, a substance that could have texture with regions of higher or lower density? This was a radical, almost unthinkable proposition. It would mean that the fundamental properties of the vacuum itself could vary from one place to another. It would shatter the elegant symmetry of our cosmological model. But as the evidence from these disparate, puzzling observations continued to mount, scientists began to look at the sky with new eyes. They were no longer just testing a successful theory. They were now actively hunting for its flaws. They started to design new surveys, new ways of mapping the cosmos specifically to search for deviations from uniformity. The question shifted from "does our model work?" to "where exactly does it break?" They began to wonder if the location of our own Milky Way galaxy, which had for so long seemed cosmically insignificant, might hold the key. Could we by sheer chance be living in a peculiar neighbourhood, a region of space where the cosmic rules were just slightly different? The whispers of rebellion were growing louder, coalescing into a chorus of doubt, setting the stage for a discovery that would force us to rethink our place in the cosmos all over again. And so the quiet anomalies that had haunted the fringes of cosmological data for years began to converge. The scattered whispers once dismissed as statistical noise or instrumental error were coalescing into a chorus singing of a profound and unsettling truth hidden in the cosmic darkness just beyond our own galactic shores. It was a moment not of a single sudden discovery, but of a dawning collective realization spreading through the astronomical community like a seismic shockwave. Teams that had been working in isolation, one group meticulously charting the positions of 1 million galaxies, another refining the universe's expansion rate to an unprecedented precision, and a third mapping the invisible scaffolding of dark matter, all found their independent lines of inquiry bending inexplicably toward the same uncharted region of the southern celestial hemisphere. It was as if 3 separate expeditions setting out to map a vast unknown continent had all stumbled upon the same monumental, impossible structure at its heart. The first pillar of this terrifying new edifice was erected not with bricks and mortar, but with the faint ancient light of countless galaxies. For over a decade, surveys like the Dark Energy Survey and the Sloan Digital Sky Survey had been engaged in the Herculean task of building a 3-dimensional map of the observable universe. You see, a photograph of the night sky is a beautiful but deceptive illusion, a flat projection of an ocean of unfathomable depth. To truly understand the universe's structure, we must know not only where a galaxy is, but how far away it is. This is the painstaking work of spectroscopy, of capturing the light from a distant galaxy and measuring its redshift, the degree to which its light has been stretched by the expansion of space-time during its long journey to us. Each redshift measurement is a sounding, a probe dropped into the cosmic abyss, giving us that crucial third dimension. The result is not a picture, but a staggering digital architecture, a virtual universe we can fly through, where galaxies are no longer points of light, but luminous markers suspended in a web of cosmic structure. Within this digital cosmos, we had long observed the grand design galaxies clustered into groups which gathered into immense clusters, which in turn were strung along unimaginably vast filaments of dark matter surrounding great voids, the deserts of the universe. This was the standard picture, the cosmic web, beautiful, and we thought fundamentally predictable. But in the data flowing from the direction of the constellation, Eridanus, this predictable pattern began to break down. The map revealed a void, yes, one of the largest ever charted, a cavernous bubble of near emptiness. Yet this was no ordinary void. The galaxies on its periphery were behaving strangely. Instead of a gentle uniform motion away from us, driven by the overall expansion of the universe, they displayed a peculiar synchronized outflow, a collective velocity that seemed to be pushing them away from the void's center, with an anomalous additional vigor. It was a river of galaxies flowing faster than the current of cosmic expansion should allow. Cosmologists stared at their simulations, at the intricate dance of gravity and expansion, and could find no explanation. A simple absence of matter could not produce this effect. An empty space doesn't push. It merely fails to pull. What they were witnessing was not an absence, but an active, repulsive presence, a ghost in the cosmic machine, exerting a subtle but undeniable pressure on everything around it. This was the first piece of evidence, a colossal map pointing a trembling finger at a place where the rules seemed different. The second pillar came from the very heart of the cosmic controversy that had divided astronomers for a generation, the Hubble tension. The persistent, maddening disagreement between the expansion rate of the universe as measured locally versus how it was predicted from the early universe's afterglow. To refine their local measurements, astronomers had turned to the unparalleled power of the James Webb Space Telescope, its infrared vision piercing through cosmic dust to gauge the distances to pulsating Cepheid variable stars and brilliant TPE-year supernovae with breathtaking accuracy. These are our standard candles, the lighthouses of the cosmic ocean. By knowing their true brightness, we can calculate their distance, and by measuring their redshift, we can determine how fast they're receding from us. This is how we build the cosmic distance ladder rung by painstaking rung to measure the local Hubble constant. As teams refined this value, a new, even more granular approach emerged. What if the Hubble constant wasn't in fact a constant? What if it varied slightly from one part of the sky to another? The idea was heretical, a direct challenge to the cosmological principle, the foundational assumption that the universe is broadly the same in all places and all directions. Yet driven by the stubborn anomalies they investigated, they aimed their instruments, including the Hubble and Webb, at the very same region highlighted by the galaxy mappers. They measured the recession velocities of supernovae exploding on the edge of that great void and within the sparse island chains of galaxies that drifted inside it. The results when they came were electrifying. Here, in this specific enormous volume of space, the universe was expanding faster. The local value of the Hubble constant was measurably, irrefutably higher than the global average. It was a stunning confirmation of the galaxy flow data. The river was indeed flowing faster. The engine of cosmic expansion, the mysterious force we call dark energy, was not a smoothly distributed uniform pressure, suffusing all of space-time. Somehow in this one gargantuan region near our own home, its influence was amplified. It was as if we had been living next to a storm system in the fabric of reality itself, a place where the gentle breeze of expansion had become a localized gale. The two most distinct and sophisticated methods of probing the modern universe were now screaming the same impossible message. The whispers had become a roar, but it was the third and final pillar that transformed a compelling hypothesis into an undeniable reality, sealing the discovery in the annals of science. This evidence came from the most subtle and ethereal of all cosmic phenomena, weak gravitational lensing. Einstein's general relativity tells us that mass warps the fabric of space-time and light. Following these warps is bent. On a cosmic scale, the immense invisible halos of dark matter that surround galaxies and clusters act as powerful lenses. The light from a galaxy, billions of light years behind such a lens, is distorted, its image ever so slightly sheared and magnified as it travels toward our telescopes. The effect on any single galaxy is imperceptible, lost in the randomness of its natural shape. But by statistically analysing the shapes of hundreds of millions of distant background galaxies, astronomers can detect a coherent pattern of alignment, a subtle preference for them to be stretched in one direction over another. This pattern allows us to build a map of what is otherwise unseeable, a direct chart of the distribution of all mass, both dark and luminous, between us and the distant universe. It is our ultimate tool for weighing the cosmos. A global consortium of lensing experts turned their attention to the Eridanus sector, painstakingly creating the deepest and widest mass map ever conceived of this region of sky. They were looking for the gravitational signature of the structures responsible for the anomalous galaxy flows. According to every known model, even a vast void, while lacking matter, is still surrounded by filaments and walls of dense dark matter. The lensing map should have shown these massive structures clearly, their powerful gravity distorting the light from behind. Instead, the map revealed something profoundly strange. The lensing signal across the entire region was weaker than in any other part of the sky. It was as if we were looking through a cosmic pane of glass that was unnaturally smooth, a region of space-time that was somehow less warped, less creased by the presence of mass. The dark matter filaments on the bubble's edge were there, but their gravitational influence was muted, as if being counteracted by an opposing force. This was the smoking gun. The phenomenon was not merely an absence of matter which would result in a lack of lensing. It was an active repulsive energy field that was smoothing out the gravitational dimples in space-time, fighting against the pull of gravity on a gargantuan scale. It was a gravitational mirage, a place where the universe's fundamental forces were in a state of bizarre and unprecedented conflict. Gravity was trying to pull things together, while this localized, amplified dark energy was aggressively pushing them apart, stretching the very fabric of reality to its limit. With the three pillars of evidence locked into place, the anomalous motion of galaxies, the locally accelerated expansion rate, and the suppressed gravitational lensing, the conclusion was inescapable, however unsettling. In a press conference broadcast around the globe, the joint committees of the major astronomical collaborations presented their findings to a breathless world. The charts and graphs, the culmination of decades of work by thousands of scientists, all told the same story. They announced the confirmed detection of a localized non-uniformity in the dark energy field, a bubble, a vast amorphous structure roughly 700 million light-years in diameter, its closest edge a mere 500 million light-years from the outer spiral arms of the Milky Way. In cosmic terms, it is our next-door neighbour, a neighbour whose existence violates our most cherished assumption about the universe, that our place in it is not special. Suddenly it was. We live on the precipice of a region where the fundamental constant that dictates the ultimate fate of the cosmos is itself not constant. They gave it an official designation, but the name that stuck the name whispered in university hallways and on late-night talk shows was the one that captured its terrifying essence, the dark energy bubble. The reaction from the global scientific community was not one of simple celebration. It was a complex tapestry of awe, disbelief, and a deep primal sense of intellectual vertigo. Careers had been built upon the bedrock of the cosmological principle of a smooth, homogeneous universe. Textbooks were written, theories were forged, Nobel Prizes were won, all under this single elegant assumption. And now that foundation had a fracture running through it, a fracture 700 million light-years wide. The first wave was denial. Rival teams scrambled to reanalyze the public data, desperately searching for a flaw, a subtle systematic error in the instrumentation, a miscalculation in the complex statistical analysis that could explain everything away and restore the comfortable familiar cosmos. They searched for a conspiracy of errors, a perfect storm of tiny mistakes, across three entirely different methodologies that had somehow mimicked this impossible signal. But the signal was too strong, the convergence too perfect. The data held. Then came the wave of bewildered acceptance, and with it a torrent of frantic activity. Theorists who had spent their lives working on beautifully symmetric models of the universe suddenly found themselves in a wild, untamed frontier. Was this a primordial fluctuation, a leftover from the chaotic moments after the Big Bang frozen into the fabric of space-time, or was it a sign of something new, a phase transition in the vacuum energy like water, turning to ice but on a cosmological scale? Could it be the influence of something from outside our known dimensions, its effects bleeding through into our reality? Every theory, from the most conservative to the wildly speculative, was suddenly on the table. The discovery of the dark energy bubble did not close a chapter in our understanding of the universe. It ripped the book apart and threw the pages into the wind. We had been staring at a single static photograph of our universe, believing it told the whole story. Now we had discovered a single frame from a cosmic movie, a frame that revealed a plot twist so profound that it redefined everything that came before and everything that might come after. We had found a monster in our own backyard. A quiet, invisible, incomprehensibly vast entity whose very existence poses the most fundamental questions we have ever dared to ask. What created it? Is it stable, or is it growing an unstoppable cancer in the cosmos set to consume everything? Are there more of them out there peppering the universe with islands of aberrant physics? And the most chilling question of all, one that now keeps cosmologists awake in the dark, lonely hours of the night: what happens if we one day drift inside? And so the signal was confirmed. In the silent, sterile control rooms of the world's greatest observatories, a collective breath was held, then released in a torrent of disbelief and wonder. For a moment there was no celebration, no triumphant announcement. There was only the profound, earth-shattering quiet that follows a revelation so fundamental it realigns our entire perception of reality. The cosmological constant, that neat, elegant and comfortably predictable pillar of modern physics, had just been fractured. The smooth, uniform ocean of dark energy we had imagined stretching across all of creation was in our own cosmic backyard doing something impossible. It was gathering. This was not a subtle deviation buried in statistical noise. It was a gravitational and energetic anomaly of galactic proportions, a bubble of space-time itself being pushed apart from within with an unnerving, localized ferocity. The very fabric of the cosmos, which we had presumed to be woven with the same thread everywhere, suddenly had a patch made of an entirely different material. The immediate aftermath was a cascade of frantic communication, a digital wildfire of data charts and half-formed hypotheses igniting across the globe. Physics departments became war rooms overnight. Whiteboards, once pristine with the tidy equations of a stable universe, were violently erased, their blankness a testament to our sudden humbling ignorance. Every assumption was now suspect. Every accepted truth was now on trial. The first question, the one that echoed in every laboratory from Pasadena to Geneva, was one of time. What is the nature of this thing's existence? Are we witnessing a fleeting temporary outburst, a kind of cosmic weather event in the vacuum of space, a violent energetic fluctuation that will dissipate back into the background, leaving no trace but our bewildered observations? If so, it would imply that the vacuum of space is not a placid void, but a simmering dynamic medium capable of spontaneously erupting with pressures that can warp the destiny of galaxies. The idea itself is terrifying. It suggests the fundamental constants of nature might not be constant at all, but subject to random chaotic change. Our universe in this view becomes a far less predictable, far less stable home than we ever imagined. We would be living not on a solid continent of physical law, but on a temporary island in a roiling sea. Or, and this was perhaps the more unsettling possibility, is this bubble a stable, long-lived structure? Is it a permanent feature of our local cosmic geography? This line of inquiry leads us down a darker, more ancient path into the very first moments of creation. Could this be a primordial remnant, a fossil from the Big Bang itself? We know the early universe was a maelstrom of unimaginable energies, a chaotic soup where the laws of physics were still settling into place. Perhaps in that initial violent expansion some regions cooled and settled imperfectly. Imagine pouring molten steel into a mould. Most of it solidifies uniformly, but sometimes an air bubble, a flaw, gets trapped within the structure. Could our dark energy bubble be just that? Cosmic imperfection, a scar from the universe's birth where the properties of space-time itself are fundamentally different. If this is a relic, an echo of the dawn of time, then it is both a treasure and a terror. It would be a preserved sample of the universe in its infancy, a laboratory for studying physics under conditions we could never hope to replicate. It would give us a direct window into the cataclysm that birthed everything we see. Yet it would also mean that the universe is not homogeneous. It would imply that there could be other such relics, other flaws in the cosmic fabric, scattered across the vast darkness between galaxies. We have built our entire understanding of the cosmos on the Copernican principle, the idea that we do not occupy a special or privileged place. But the existence of a local stable bubble of exotic energy shatters that principle. We would be by definition living in a very special, very strange, and potentially very dangerous place indeed. The very ground of our cosmic existence would be revealed as fundamentally uneven. This initial schism, transient storm versus ancient fossil, drove the first wave of frantic research. But as theorists grappled with the data, a third more radical possibility began to emerge, whispered at first, then debated with growing urgency. What if the bubble is neither a temporary fluctuation nor a relic of the past? What if it is something new, something active? What if it is evidence not of a flaw in the universe, but of a flaw in our understanding of it? This is the door to new physics, a door that has been locked and barred for nearly a century, and this discovery was the key that finally irrevocably turned in the lock. The very foundation of our cosmic model, Albert Einstein's theory of general relativity, and the standard model of particle physics that grew from it, cannot account for this. There is simply no room in the mathematics for a localized concentrated sphere of dark energy. To explain it, to even begin to comprehend it, we must imagine things that until now have lived only in the realm of speculative fiction. The first and most promising candidate is that dark energy is not a constant at all. It is not a static property of space, but a dynamic evolving field that permeates the entire universe, much like a magnetic field. Theorists have a name for this hypothetical entity, quintessence. Unlike the cosmological constant, a quintessence field can change over time and crucially vary from place to place. It can have currents, eddies, and waves. It can possess potential energy like a coiled spring and kinetic energy like a moving object. In this model, our bubble is no longer a passive object. It becomes a place where the quintessence field has become excited, a region where its energy density has soared, pushing space-time apart with an amplified force. This concept is both elegant and profoundly complex. It would mean that the accelerating expansion of the universe is not a simple single-speed process. Instead, it would be governed by the behavior of this unseen field, a cosmic energy field that is in a very real sense alive. It raises a cascade of new questions. What particle is associated with this field? The standard model has its photon for electromagnetism, its gluon for the strong force. A quintessence field must have its own fundamental particle and undiscovered quantum entity that carries this repulsive force. Finding such a particle would be a monumental achievement on par with the discovery of the Higgs boson, but its properties would be far stranger. It would be a particle that interacts almost exclusively with the structure of space-time itself, a ghost in the cosmic machine. And if this field can become concentrated here, what is causing it to do so? Is there some unknown source, some exotic object at the bubble's center, leaking this energy into the quintessence field? Or did a wave of energy traveling from some distant violent event pass through our region of space, causing the field to ripple and crest into the bubble we now observe? We are forced to consider physics. We have not yet dreamed of interactions that operate on scales far beyond our current comprehension. The bubble becomes a symptom of a deeper, more active and more intricate cosmic reality. It's as if we have spent our entire history studying the placid surface of an ocean, only to suddenly see the back of a colossal unknown creature breach the waves before us. We now know the depths hold something more. But even this radical idea of a dynamic energy field might not be radical enough. Some physicists are looking at the problem from the opposite direction. What if the energy is not the problem? What if the problem is gravity? For over a century, Einstein's general relativity has been our undisputed champion. It has predicted everything from the bending of starlight to the existence of black holes and the subtle ripple of gravitational waves. It has passed every single test we have thrown at it. But all of those tests have been conducted here within our solar system, or by observing distant but discrete objects. We have never been able to test it on the scale of an entire supercluster of galaxies with this level of precision. Perhaps on these truly mind-boggling scales, Einstein's beautiful theory begins to break down. This is the realm of modified gravity. These theories propose that on very large distances or under conditions of very low acceleration, the force of gravity does not behave as Einstein predicted. They add new terms to his equations, subtle modifications that are completely undetectable in high-gravity environments like a solar system, but which become dominant in the vast empty spaces between galaxies. In some of these models, the effect we call dark energy isn't an energy at all. It is an illusion, a ghost created by our misunderstanding of the true nature of gravity. It is the force of gravity itself acting in a strange and repulsive way over immense distances. If this is the case, then our bubble is not a bubble of energy. It is a bubble of law, a region of space where the fundamental properties of gravity are manifesting in an extreme and visible way. It would be a place where the rules are different. This is a concept so profound it borders on the philosophical. It suggests that the laws of physics may not be universal. The elegant mathematical structure that governs a falling apple on Earth and a swirling galaxy a billion light-years away might have fine print exceptions and clauses that only apply in certain cosmic zip codes. Our bubble would be the first concrete evidence that we live in a universe with a far more complex and perhaps even localized legal system than we ever dared to imagine. It is a possibility that makes many physicists deeply uncomfortable, as it strikes at the very heart of the scientific endeavor, the search for universal unchanging laws. Faced with this dizzying array of possibilities, a cosmic storm, a primordial flaw, a new energy field, or a crack in Einstein's theory, the scientific community did the only thing it could. It began to design new ways to see. The race was on a frantic, collaborative, yet fiercely competitive scramble to devise the next generation of experiments to point our existing instruments in new directions, to find a way to dissect the bubble and force it to reveal its secrets. The first challenge is to map its boundaries with perfect precision. Is it a perfect sphere as the initial data suggests? Or are its edges ragged and diffuse like a cloud? A perfectly spherical shape might hint at a central source, perhaps some exotic object like a cosmic string, or a domain wall bleeding energy into the surrounding space. A more irregular shape might favour the fluctuation model, the result of a chaotic weather-like process. Teams began requisitioning telescope time, aiming everything from the James Webb Space Telescope to the vast radio arrays in Chile and South Africa at the regions of sky just inside and just outside the bubble's edge. They are looking for subtle distortions in the light from distant galaxies as it passes through the boundary, searching for the unique gravitational lensing signature that a new theory of gravity might produce. Others are reanalyzing the cosmic microwave background radiation, the afterglow of the Big Bang, looking for any temperature anomalies, any faint shadow that the bubble might have imprinted on the universe's baby picture nearly 14 billion years ago. If the bubble is a primordial relic, a signature of its existence might be hiding there in the oldest light in the cosmos. Simultaneously, theoretical physicists have returned to their blackboards, their pens, and their supercomputers. They are building models running simulations of universes with dynamic quintessence fields, with modified gravity, with trapped primordial defects. They are trying to find a mathematical framework, however strange, that can produce a structure like the one we have found, without breaking all the other known rules of the cosmos. Each potential theory makes slightly different predictions. A quintessence model might predict that the bubble should be oscillating ever so slightly in its intensity. A modified gravity theory might predict that galaxies on the edge of the bubble should be moving in a very specific anomalous way. Each prediction is a target, a clue for the observers to hunt for. This is the very essence of the scientific method accelerated to a breakneck pace, by a discovery that touches everything we thought we knew. It is a dialogue between the thinkers and the seers, a rapid-fire exchange of ideas and data, all driven by a singular obsessive need to understand, because the stakes are far higher than just solving a cosmic puzzle. The nature of this bubble has profound implications for the ultimate fate of our universe, and perhaps for our own future within it. If it is a temporary fluctuation, we may have witnessed a rare and spectacular but ultimately harmless cosmic light show. But if it is a stable feature, a sign of new physics or a warp in the laws of nature, then we are faced with a new and uncertain reality. The existence of this one bubble forces us to ask, are there others? Is the universe filled with these energetic pockets, some perhaps pushing space-time apart, others frighteningly pulling it together? Could two such bubbles collide? What would happen if a galaxy, or even our own Milky Way, were to drift into a region where the laws of physics were subtly or catastrophically different? We have been thrust without warning from an era of cosmic certainty into a new age of profound and thrilling uncertainty. Every direction we look now holds a question. Every new piece of data is a potential key or another layer of the enigma. The quiet, predictable cosmos is gone. In its place is a universe far more complex, far more mysterious, and far more alive than we ever dared to believe, and out there in the darkness just beyond our galactic shores, the bubble waits a silent, shimmering testament to our own infinitesimal understanding of the grand, terrifying, and beautiful cosmic whole. The data was undeniable, a scar burned into the fabric of space-time. Staring back at us from the ghostly light of distant galaxies was an impossibly vast sphere of influence, an anomaly that had no right to exist. The bubble was real. For the teams of scientists who had spent years chasing these subtle phantoms in the cosmic microwave background, and the meticulous redshift survey's confirmation was not a moment of pure triumph. It was the beginning of a profound intellectual crisis. The map of the cosmos we had so carefully drawn was not just incomplete, it was in a fundamental way wrong. The discovery shattered the comforting illusion of a uniform universe, replacing it with a far stranger, more unsettling picture. In conference halls and university classrooms across the globe, a single terrifying question echoed, "What in the universe is SEMD?" And answering that question would not be a simple matter of observation. It would require a battle of ideas, a clash of theories at the very edge of human knowledge. The first and most conservative explanation to emerge was perhaps the most intuitive, an attempt to explain the extraordinary, without resorting to exotic new physics. This was the cosmic void hypothesis. We know the universe is not perfectly smooth. It is a tapestry of unimaginable scale, woven from threads of galaxies and dark matter, separated by colossal chasms of near-nothingness. These voids are the great deserts of the cosmos, regions where matter for billions of years has been swept away by the relentless pull of gravity from surrounding superclusters. The argument was simple, elegant even. Perhaps our local group of galaxies resides on the edge of one such monumentally enormous void. Inside this underdense region, there is simply less matter, less gravitational glue holding things together. With the gravitational brakes weakened, the ever-present outward push of dark energy would not need to be stronger. Its effects would merely be more pronounced. It would be like trying to run on solid ground versus running through deep water. The force you exert is the same, but the resistance is vastly different. From our perspective peering into this void, it would appear as if space itself were accelerating away at a far more aggressive rate. The bubble in this model was not a source of new energy, but a cosmic magnifying glass revealing the true unhindered face of dark energy, in a region where gravity had lost its grip. It was a compelling idea, one that kept our existing model of the universe, the lambda CDM model, largely intact. It required no new particles, no new forces, only an extreme and statistically improbable arrangement of the things we already knew existed. Yet as the data from the bubble's boundary was refined, this conservative explanation began to show cracks. The models predicted that the transition from the normal universe into a void should be gradual, a gentle slope of decreasing matter density. The bubble, however, possessed an edge, a terrifyingly sharp edge. The galaxies at its perimeter were being accelerated with a uniformity and coherence that defied the messy, chaotic nature of a simple void. Furthermore, the sheer scale of the required emptiness was staggering, far larger than any known void, and bordering on the statistically impossible. To accept the void hypothesis, we would have to accept that we live in one of the most unusual 1 in a billion locations in the entire observable universe. For many scientists, this violated a core principle, the Copernican idea that we are not special. It felt less like an explanation, and more like an appeal to cosmic coincidence. The safe harbour of known physics was proving to be a treacherous one, and the community, with a mix of excitement and trepidation, began to steer its collective intellect toward more radical shores. If the bubble wasn't an absence of matter, could it be the presence of something entirely new? This question gave birth to the second great contender, the fifth force. For a century, we have understood the universe to be governed by 4 fundamental forces. Gravity, the grand architect of cosmic structures, electromagnetism, the engine of stars and the medium of light, and the 2 nuclear forces, strong and weak, which bind the hearts of atoms. This quartet of interactions has explained almost everything we've ever observed. But what if there is another, a 5th interaction? A ghost in the cosmic machine operating on scales so vast that it has remained hidden until now. In this theoretical framework, dark energy is not the cosmological constant that Einstein envisioned, an intrinsic energy of empty space itself. Instead, it is a dynamic evolving entity known as quintessence. This quintessence would be a field much like a magnetic field that permeates all of space. And like any field, it could have fluctuations. It could have regions where its energy is higher or lower. The bubble then would be a domain where this quintessence field is in a different state, a pocket of the universe where the 5th force that mediates this field is switched on in a new way. This was a breathtakingly audacious idea. It proposed that the fundamental laws of nature might not be the same everywhere. Inside the bubble, this 5th force would actively repel matter and energy, a kind of anti-gravity that supplements the background push of dark energy, creating the hyper-acceleration we observe. The sharp edge of the bubble was no longer a problem. It was a key piece of evidence. It could be a phase transition, like water freezing into ice along a sharp boundary. The universe inside the bubble would be in one energetic state, and the universe outside would be in another. We wouldn't just be living near an anomaly, we would be witnesses to a fundamental crack in the bedrock of physics. This model was seductive in its explanatory power, fitting the peculiar geometry of the bubble with unnerving precision. It turned the feature from a problem into a prediction. But it came at a steep price. If this new force exists, why have we never detected it in any other experiment? Why is it confined to this one region of space? Proponents argued that the force might only couple to matter under extremely low density conditions, making it invisible within galaxies or solar systems, only revealing its true nature in the desolate expanse between the star cities. It was a theory both beautiful and maddening, postulating a new chapter of physics that was for now written in a language we could not yet read in a book we had only just discovered. The debate raged, an intellectual firestorm that consumed cosmology. Yet even the radical notion of a 5th force seemed tame compared to the ideas brewing at the furthest frontiers of theoretical physics. From the esoteric world of string theory came a proposal that was almost mystical. String theory posits that the reality we experience are 3 dimensions of space, and one of time, is but a sliver of a much larger, higher dimensional reality called the bulk. Our universe in this view is a membrane floating within this multi-dimensional space. What if the theorists asked our brain was not alone in the bulk? What if another brain, another universe had drifted impossibly close to our own? The intense acceleration within the bubble would not be from a force within our universe, but the gravitational leakage from this other reality, a phantom gravity bleeding through the dimensions to push our local region of space-time apart. The bubble's edge would be the point of closest approach, the shimmering boundary where the veil between worlds grows thin. It was a concept of such staggering grandeur that it bordered on science fiction, a universe of cosmic echoes and invisible companions. And from another corner came the champions of modified gravity. Theirs was perhaps the most intellectually defiant stance of all. They argued that there is no bubble, there is no dark energy, there is no 5th force. The entire phenomenon, they claimed, is a grand illusion, an artifact. a ghost created by our own incomplete understanding of the most familiar force of all gravity. General relativity, Einstein's masterpiece, has been tested and proven to exquisite precision within our solar system and in the dance of binary pulsars. But what if it breaks down over immense intergalactic distances? Modified gravity theories propose that on the scale of 1 billion light-years, gravity does not behave as Einstein predicted. It weakens faster than we expect, or it can even become repulsive under certain conditions of ultra-low density. The bubble in this view is simply the region where we are seeing this modified law of gravity in action. It is not an object, but a feature of the law itself, a gravitational mirage conjured by our flawed equations. We invented dark energy, they argue, to patch a hole in a theory that is ultimately broken. This was the ultimate heresy, a challenge to the century-old foundations upon which all of modern cosmology had been built. It was also for many a step too far, as modifying gravity without breaking all the things it gets right has proven to be a Herculean, perhaps impossible theoretical challenge. 4 distinct possibilities: a void of impossible scale, a new force of nature, an echo from another dimension, a crack in Einstein's theory of gravity. The scientific community was fractured, with brilliant minds defending each position with fierce intellectual rigour. The data was being sliced, diced and reanalyzed in 1,000 different ways, each team searching for a smoking gun, a single data point that could shatter one theory and elevate another. The deadlock seemed absolute, a testament to the profound mystery the universe had placed before us. For months it felt like cosmology was adrift in a sea of speculation, with no clear path forward. Then a breakthrough came from an unexpected quarter. Not from a new telescope or a grand experiment, but from the quiet hum of supercomputers running simulations of unprecedented complexity. A team of astrophysicists was modelling not just the bubble's expansion, but the subtle, intricate motions of the dwarf galaxies orbiting our own Milky Way and the delicate filaments of gas that connect us to the Virgo supercluster. They were treating our local cosmic neighbourhood as a single gravitational system, a sensitive seismograph for the bubble's influence. Their simulations, running for months, tested each of the 4 leading hypotheses. The void model couldn't reproduce the fine-grained velocity patterns. The gravitational tides it created were too gentle, too diffuse. Modified gravity theories, when calibrated to create the bubble, threw the internal dynamics of our own galaxy into chaos, a clear contradiction of observation. The brain-world scenario, while poetically compelling, offered no unique testable signature in the local galaxy flows. But the 5th force model, the one with a quintessence field undergoing a phase transition, did something remarkable. When the simulators programmed in the sharp boundary, the phase transition edge, the model didn't just create the bubble, it predicted the existence of a faint but detectable shock wave, or domain wall, at the perimeter. This was not a wall of matter, but a wall of pure force, an invisible line where the laws of nature changed. This wall would exert a tiny, almost imperceptible gravitational influence on the objects nearest to it. It would slightly but systematically alter the orbits of the outermost satellite galaxies of the Milky Way. It would gently shepherd the streams of interstellar gas, aligning them in a way that pure gravity could not. With trembling hands, the team compared the simulation's predictions to the real-world observational data, the painstakingly collected maps of our galactic halo. And there it was. Hidden in the noise overlooked for years was a subtle, coherent alignment in the orbits of the most distant globular clusters and dwarf galaxies. An anomalous drift, a collective motion that had defied all previous explanation. It was the echo of the wall, the faint gravitational whisper of the bubble's edge, precisely as the 5th force model had predicted. It was the smoking gun. The moment was not one of loud celebration, but of a quiet collective intake of breath across the entire field. The pieces clicked into place, not with a triumphant bang, but with the profound and chilling resonance of a deep truth revealed. The other theories, while brilliant in their conception, were suddenly rendered obsolete, elegant explanations for a phenomenon that now had a far more specific, far more tangible cause. The intellectual fireworks had ended, and from the smoke, a single terrifyingly beautiful idea had emerged, scarred with the evidence of its victory. We are forced now to confront a universe far more complex and mutable than we ever dared to imagine. The comforting bedrock of physical constants and universal laws has been shaken to its core. We have discovered that dark energy is not a simple unchanging energy of the vacuum, a placid constant driving a stately expansion. It is a dynamic field, a seething ocean of potential that can change its state, creating borders and domains where the cosmos operates under different rules. The bubble is not just a place, it is a state of being. And its existence forces the most profound question of all. Is this a singular freak occurrence, a fossil from the chaotic early universe? Or is the cosmos riddled with such domains, a patchwork quilt of different physical laws? The smooth, predictable universe of the 20th century is gone, replaced by a picture of violent ongoing change. Our cosmic map is not just being redrawn, it is being ripped up and replaced with a tapestry of unknown wonder and terror. We have found the bubble, but in doing so, we have come to realize that we may be fundamentally lost facing a new cartography of reality itself. And the only way forward is to build the instruments and launch the missions capable of mapping this new wilder cosmos, to go hunting for the edges of other worlds hidden within our own. And so we are left here adrift in the sudden silence that follows a revelation of this magnitude. The cosmic symphony we thought we knew, a grand sweeping composition governed by universal laws, has been interrupted by a single discordant impossible note. A note played right next to us, this bubble of dark energy. This ghost in the local cosmos is not merely an addendum to our astronomical charts. It is a profound and unsettling tear in the very fabric of our most cherished cosmological assumption that the universe on its grandest scales is the same everywhere. For a century we have held this idea, the cosmological principle, as our compass, our guide through the bewildering darkness. It was a comforting thought, a declaration of cosmic democracy. It meant that the slice of the universe we can see is a fair sample of the whole magnificent unending tapestry. It allowed us to take the light from distant galaxies, the faint afterglow of the Big Bang itself, and from them confidently write the biography of everything. We built our standard model of cosmology upon this solid bedrock, a model that told a story of a universe born in fire, expanding, cooling, and now mysteriously accelerating. Dark energy was the name we gave to that mysterious accelerant, a phantom energy woven uniformly through the vacuum of space-time itself, pushing everything apart with a gentle, inexorable pressure. We imagined it as a placid, featureless ocean, its tide rising at the same rate from one edge of creation to the other. Our discovery, the one we have journeyed toward throughout this exploration, changes the character of that entire ocean. It tells us that here in our own cosmic neighborhood the tide is different. The pressure is higher. The ocean is not placid. It has currents, eddies and storms. We find ourselves living inside one of its great maelstroms. This is a shift in thinking as monumental as earth-shattering, as when we first realized the Earth was not the center of all things. In a strange and ironic twist, we're once again forced to confront the possibility of our own special place in the cosmos. Not a place of divine privilege, but one of bizarre cosmic anomaly. The Copernican principle, the idea that we are not special observers, has been the engine of scientific progress for 500 years, pushing us away from self-centered cosmologies. Now, we must grapple with a universe that might in fact have local peculiarities, provincial bylaws written into space-time. It challenges the very notion of a universal now or here, suggesting that to truly understand the cosmos, you might first need to know your own cosmic address, with a precision we never thought necessary. Physicists and astronomers around the world are now grappling with the sheer audacity of what this implies. Is our bubble a remnant of the chaotic early universe, a fossil of some ancient quantum fluctuation that never smoothed out? Or is it something being actively generated, a consequence of some new physics we have yet to even imagine? Could it be related to the nature of dark matter itself? Another profound mystery suggesting the two great darknesses are locked in a more intimate and complex dance than we ever knew. These questions are not academic. They strike at the heart of our quest to understand reality. Because if the universe is not uniform, then our measurements of its age, its expansion rate, and its ultimate destiny might all be subtly, or perhaps dramatically skewed by the properties of our own atypical home. We have been looking at the entire cosmos through a distorted lens, a lens forged by the very bubble we were unaware of, and we are only now beginning to perceive its warp. The great challenge has been thrown down, the anomaly has been detected. Now the real work begins to map its shores, to plumb its depths, and to understand its nature. This is a task that will push our technology and our ingenuity to their absolute limits, and we are already preparing for the voyage. Across the high, arid deserts of our world, new eyes are being prepared to open to the sky. The Vera C. Rubin Observatory, a titan of glass and steel, will soon begin its legacy survey of space and time. For a decade, it will scan the entire southern sky every few nights, creating the deepest, most detailed motion picture of the universe ever made. Its unprecedented sensitivity will allow us to chart the positions and movements of billions of galaxies with pinpoint accuracy. Within that torrent of data, we will search for the gravitational effects of this dark energy bubble on a colossal scale. We will see how it warps the paths of galaxies behind it, how it subtly shifts the light from distant supernovae. The observatory's mission is no longer just to map the cosmos as it is, but to map the very gradient of its weirdness, to trace the invisible boundary where our bubble of high energy density fades back into the calmer seas of the wider universe. Far above the blurring haze of our atmosphere, a new generation of sentinels will join the hunt from the silent clarity of space. The Nancy Grace Roman Space Telescope, with a field of view 100 times larger than Hubble's, will conduct a cosmic census on a scale previously thought impossible. It is designed specifically to tackle the mystery of dark energy, and now it has a prime, tangible target. It will stare into the deepest reaches of our local supercluster, measuring the precise rate of expansion within and beyond the bubble's edge, testing to see if the Hubble constant, our measure of cosmic expansion, is truly constant at all, or if it changes depending on where you look. Europe's Euclid satellite, another powerful dark universe detective, will create a 3D map of the cosmos, looking for the telltale signature of the bubble's influence on the large-scale structure of the universe, the great cosmic web of galactic filaments and voids. These observatories are not just telescopes. They are cartographers of the unknown, designed to draw the first reliable maps of this new alien territory that we have discovered wrapped around our own galactic home. Their combined power represents a full-scale assault on this mystery. We will probe the bubble with light, with gravity, with the standard candles of exploding stars and the standard rulers of cosmic sound waves. We will seek its edges, measure its strength, and hunt for its siblings. For if there is one such bubble, could there not be others? Does our universe resemble a placid lake, or is it more like a simmering pot, filled with bubbles of varying energy, densities constantly forming and bursting in a process far more dynamic and violent than our serene models predicted? Finding another bubble would transform this discovery from a local anomaly into a fundamental feature of the cosmos, forcing a complete rewrite of the laws of cosmology. The search is on a search that extends beyond mere observation. In the subterranean quiet of laboratories deep underground, physicists are designing experiments to hunt for the particles or fields that could give rise to such an entity. They will collide matter at unimaginable energies, hoping to catch a fleeting glimpse of the physics that governs the vacuum of space-time itself, searching for clues to why it possesses this strange anti-gravitational energy at all, and why that energy might not be constant. And as we probe this enigma, we are forced to confront the ultimate question it poses: what does this mean for our future? For the final act in the long story of the cosmos, our predictions for the end of everything have always been based on that crucial assumption of uniformity. If dark energy were a constant gentle pressure, the universe would likely expand forever into a big freeze, a future of cold, dark, and eternal emptiness, as everything recedes from everything else until the last light flickers out, a lonely but peaceful end. But if dark energy can change, if it can be concentrated in bubbles like the one we find ourselves in, then all bets are off. The future becomes a far more uncertain and potentially violent place. What if our bubble is not stable? What if it is growing? If the density of dark energy within it were to increase, the repulsive force could become so strong that it would overwhelm not just the gravity between galaxies, but all other forces. This is the scenario known as the Big Rip. It would be an unmaking of staggering proportions. First, our own Milky Way would be torn apart, its stars flung into the void. Then solar systems would be unbound planets cast away from their suns. Eventually, the very fabric of matter would fail. Planets, stars, and even the atoms that make up our bodies would be ripped asunder in the final terrible moments of existence. Our bubble, our seemingly innocuous cosmic anomaly, could be the seed of the universe's ultimate destruction. Alternatively, what if the bubble collapses? What if this higher energy state is unstable, a temporary fluctuation that is destined to decay back to a lower energy vacuum? Such a collapse could propagate outwards at the speed of the light, a wave of cosmic phase transition that rewrites the laws of physics as it passes. The universe beyond the wave would be utterly alien, perhaps incapable of supporting the structures or the life we know. We would have no warning, our existence would simply be extinguished as the very nature of reality itself changed around us. From the cradle of a quiet cosmic neighbourhood, we have suddenly been shown that we may be living on the shores of a treacherous and unpredictable sea. The discovery of this bubble doesn't just give us a new object to study, it infuses our cosmology with a sense of urgency, of profound drama. The fate of the universe is no longer a distant, abstract calculation. It has become a local story, a pressing investigation whose outcome has direct consequences for our own remote future. This is why we continue to look up. It is why we build these incredible engines of discovery, not just to satisfy our curiosity, but because it is one of the most fundamental expressions of the human spirit. We are a species defined by our refusal to accept the horizon as a boundary. From the moment our ancient ancestors first looked at the stars and wove them into stories of gods and monsters, we have been on an unbroken quest to understand our place. We mapped our world, then our solar system, then our galaxy. Each step revealed a universe far larger and more complex than we had ever dreamed. And at every stage we have been humbled. We have been forced to abandon our preconceived notions, our comforting certainties, our sense of centrality. This latest discovery is simply the next great humbling. It is a reminder from the cosmos itself that our knowledge is a small island in a vast, uncharted ocean of ignorance. And it is the shores of that island that are the most exciting place to be. It is where the waves of mystery break, where the thrill of exploration calls to us. We have peered into the darkness and found not the simple uniformity we expected, but a rich, textured and living cosmos, a place of local character and hidden complexities, a universe that is still being born, still evolving, still capable of astonishing us. Our journey has not ended. It has just taken a dramatic, unforeseen turn. The simple map has been torn up, and we are now tasked with drawing a new one, a map that includes this strange new continent of energy floating in the cosmic sea. The path forward is uncertain, the answers hidden behind a veil of deep time and unimaginable distance. But we will continue to ask the questions, we will continue to build the tools, and we will continue to listen with humility and with awe to the profound and unsettling story. The universe is trying to tell us a story that has turned out to be far stranger, more dynamic, and more magnificent than we ever had the courage to imagine.